Okay, good day, everyone. Thank you for joining us for the first installment of our 2025 webinar series. My name is Lori McLeod. I'm the president of NOVONIX Battery Technology Solutions, and I'll be your moderator for our webinar today. In just a few moments, we'll be hearing from Dr. Mark MacArthur, Director of Research and Development at NOVONIX Battery Technology Solutions. Since 2020, Mark has led the cathode materials team in Nova Scotia, focusing on developing and scaling up our patented all-dry, zero-waste cathode synthesis technology. Prior to his role with NOVONIX, Mark worked at Tesla, uncovering new lithium-ion battery materials and technologies for the EV and ESS sectors. Today, Mark will be discussing NOVONIX NMC cathode material, highlighting performance along with potential cost and environmental advantages that accompany our patented all-dry, zero-waste technology. So following the presentation, we will leave some time for questions. You can leave them directly in the Q&A feature at the bottom of your screen, and we'll respond to as many as we can. So thanks for joining, and I'm going to hand it over to Mark.
Thanks for that introduction, Lori. I'm just going to share my screen, which is displaying correctly. Excellent. Yeah, I'm excited to actually deliver the inaugural web-based seminar series that NOVONIX is putting on. The first issuance is on actually our cathode materials program that I've been leading up, as Lori mentioned, since 2020. And today my seminar is on all-dry, zero-waste cathode synthesis, a technology-enabling solution to sustainable, low-cost materials production for the lithium-ion battery industry. Slide. And as usual, I'll begin with the obligatory size 8 font disclaimer that everybody needs to review diligently. And as we're ready to go, we'll start with a quick overview. And just to let you all know a little bit more about NOVONIX. So NOVONIX is a battery and technology company providing revolutionary solutions to the battery industry that truly enable the adoption of clean energy at a global scale. The company is really made up of 3 major divisions from left to right. We'll go through them very briefly. Our anode materials business is located in Chattanooga, Tennessee in the United States. And we're a leading domestic supplier of battery-grade synthetic graphite. We're actually the first large-scale and sustainable production company to generate synthetic graphite to truly advance the North American battery supply chain. And we're strategically positioned to accelerate the clean energy transition through our proprietary technologies, our advanced research and development, and our partnerships. In the middle of the slide, I'm showcasing our Battery Technology Solutions division. And the photograph that's actually in the upper middle of this slide is the building in which I'm presently sitting. We're located in Nova Scotia, Canada, and we provide industry-leading ultra-high precision coulometry equipment, as well as R&D services using and leveraging our in-house pilot line, our cell testing capabilities, and our consulting expertise to really accelerate customer development programs. And what we're here to discuss today is the division I'm showcasing on the right-hand side of the screen, NOVONIX Cathode Materials. We're also located in Nova Scotia, Canada, and we're presently commercializing our patented cathode synthesis technology. This process technology minimizes environmental impacts while also, as I will demonstrate shortly, produces high quality, high performance materials. So we never sacrifice on material performance. And we do this through production of, at least at the pilot scale, material synthesis with our demonstration facility here with a nameplate capacity of 10 tons per year. So before I get into the meat of my presentation, I do want to discuss one critical item about cathode materials. So we often hear of some terms getting confused in the industry whenever the word dry cathode is brought up. I do want to distinguish between what is meant by dry cathode powder as well as dry cathode electrode, because both kind of get mixed up occasionally. So dry cathode electrode is a process whereby you take standard cathode active material and produce a freestanding dry electrode. Typically, that could be a cathode material, an anode material, which then gets laminated onto a foil current collector before being assembled into a battery cell. Dry cathode material on the other side is a dry powder technology. We are producing the powder in a completely dry state. Both methods, both dry methods, are actually compatible with one another. In fact, dry cathode powder can be utilized as an input for dry cathode electrodes. So you can see there is a synergy between both processes, but we are focused at NOVONIX on dry cathode powder production and technologies related to their synthesis. Before going further, I do want to touch on a little bit of market conditions when it comes to the cathode active material landscape. This may not be new information for a lot of participants on the call, but for some it may be useful to set the groundwork for what we're going to discuss further. So the opportunity for the materials market, especially in the cathode side, is actually quite large. Depending on the market reports you're reviewing, in 2024, the global cathode active material market was estimated to be roughly $27 billion, and that was forecasted to eclipse $100 billion by the end of the decade. And there are two main cathode active materials which are utilized in lithium-ion battery technologies today. One is iron-based LFP, or lithium iron phosphate type, and the other is nickel-based cathode materials, or NMC, NCA type, where you have nickel, manganese, cobalt, or nickel, cobalt, aluminum. Depending again on which market report you're reviewing, the nickel-based cathode materials truly represent around 30 to 50% of the overall total cost structure of a battery cell. And that's illustrated by my pie chart in the upper right side of the screen. In this case, 44% of the cost structure is represented by NMC cathode materials. One of the biggest problems with NMC production is actually the process itself. For each ton of cathode powder, you generate approximately 3,500 to 15,000 liters of wastewater, and also a byproduct called sodium sulfate, and that could be in excess of 1 to 2, even 3 to 4 tons of waste byproduct is generated per ton of NMC cathode material, which is problematic. Small quantities of sodium sulfate on its own is really not an issue. However, when you're really feeding the gigafactories of the world with cathode active material, you really do end up having to consider all of the waste streams associated with your product and how you actually safely and responsibly dispose of some of those waste byproducts. So what you'll see is whenever you're building a gigafactory to make cathode material, you really need to consider the cost of waste. And talking a little bit about the process, when I think at least how you actually make a finished NMC cathode active material, I largely break it down into 3 steps. The first step is mining and refining your raw materials. The second step is to produce a PCAM, a precursor cathode active material. And then the third step is to convert that precursor material into a finished cathode active material. What we do at NOVONIX is eliminate that second step. We are a precursor-free process to go directly from the raw material feed to a finished cathode active material. And this technology that we have developed since 2020 really offers higher yields at lower cost and doesn't generate any wastewater because you don't consume any water in the process to make the material. Also, we can use flexible input materials, which ends up being quite advantageous. And I'll get into a little bit of why on the next slide. So again, I like to compare our process to what is conventionally done. And here I'm focusing in on the precursor synthesis process, that PCAM step I mentioned earlier. To make a precursor cathode active material, You really take metal sulfate containing materials, so a cobalt sulfate, manganese sulfate, nickel sulfate, and combine that with water in a continuous stirred tank reactor at elevated temperature. To that, you're also adding some complicated reagents, including sodium carbonate, ammonium hydroxide, and more water. So within your reaction vessel, you precipitate out your precursor. All of those metals in the metal sulfates really combine to make an intimately mixed metal hydroxide. And that is your output. However, your output still contains water, it still contains some waste. There's a few unit operations that have to be done before you can actually utilize your PCAM, your NMC hydroxide in this case. There's washing and filtering steps, which require additional water, generates further wastewater streams. And you're also making a few heavy metals along the way that need to be carefully considered before discharging into the water table. Eventually, you end up in a state where you have a PCAM powder, a NMC hydroxide, typically. You can then take that powder, combine it in a mixer with a lithium source, typically lithium carbonate, lithium hydroxide, and then you conduct the lithiation step, the step where you take the PCAM and turn it into a CAM, NMC material. So powder is loaded typically into a kiln. What's used conventionally is a roller hearth kiln. And then there are some further downstream processes to de-agglomerate the powder, get it into the shape that you want. And also you have the option of finishing it up. What I mean by that is adding any secret sauce dopants or surface coatings before you can have a fully fledged NMC powder ready to go into a cathode electrode to put into a battery cell. The NOVONIX process is quite a bit different. We start with a flexible feedstock going as far upstream as we possibly can. We like to use nickel metal powders, cobalt metal powders, their oxides, carbonates, etc. And we combine everything in a dry step, a single dry process. So not only do we have our nickel, manganese, and cobalt feedstocks in our initial step that I'm showing here, it also includes the lithium source, any dopants that are of interest. And then what we do is we perform the all dry, zero waste process. It's a relatively simple flow sheet. However, simple doesn't mean easy. There's a lot of know-how and IP in this step alone. And after we conduct this combining process, we have a powder that is ready to be loaded into a kiln. So everything downstream of this combining step is really same for same from what is done conventionally. We're still heating the material, we're still de-agglomerating, and we have the option of adding surface coatings and other treatments if we so desire. And at the end of the day, what we're left with is a free-flowing single crystal NMC powder. And we're doing that without any metal sulfates, so we're avoiding sodium sulfate waste streams. We're not using any complex reagents. There's no ammonium hydroxide, and I'll get into an advantage soon about why that's important. And we're not generating any process water waste. And what I'll show you at the tail end of my presentation is we're able to produce a material which has comparable electrochemical performance to a conventionally made NMC powder. And ultimately, we eliminate an entire factory. We're not doing PCAM production, so we don't need a PCAM factory. So that's fantastic. So all of these advantages I am telling you and NOVONIX is telling you. However, we're a little biased. What we really wanted to do was ensure that our claims were correct. So we engaged Hatch, an engineering firm that's well respected in the industry, to perform for us a process comparison study to really contrast our NOVONIX all-dry, zero-waste cathode synthesis process against conventional cathode manufacturing. And this was done at an FEL1 level. So the results from this study indicate that by going all dry, you have the advantage of decreasing the capital intensity of the process by roughly 30%, decreasing the operational expenditures by roughly 50%, and improving the environmental footprint of the overall process. So how do we do this? Well, when you look at the process flow I showed very simply on the previous slide, you get an idea of fewer unit operations that really leads to lower to no processing reagent costs, lower power consumption, lower maintenance, lower operator count, for example. All of this really accumulates to having a lower cost process. And also, by avoiding precursors which are in a hydroxide phase, you can actually improve the calcination of your entire process. You're not spending a lot of power to really make water, since you're already starting in either a metal or an oxide form. So there's lots of advantages in terms of cost saving by going with an all dry, zero waste process. And the environmental side, because we're decreasing so many unit operations, we're also lowering our power consumption and hence direct CO2 intensity. We're also looking at a lower water usage, roughly 65%. So you may ask, why is that 65% and not 100%? As you scale the equipment, as you scale the assets that are on the ground, they generate a lot of heat. So you do need some water to maintain an adequate temperature of the equipment that's on the floor. This water, however, never touches the powder. It's truly a dry process. So the water that I'm indicating here is exclusively used for cooling equipment. We're also eliminating the production of sodium sulfate waste, which I mentioned before is a large environmental problem. And remember ammonium hydroxide? Well, because we don't use it, we don't actually have to worry too much about ammonia capture. So that really makes our process safer for the employees working on the floor. And I did touch on this earlier. So NOVONIX is coming in with a very strong IP position on our all dry, zero waste process. We have several impactful cathode materials and process claims in our patent set. And we're actually the earliest to adopt all dry processing technology for the production of NMC. We cover a single step to produce our materials. We are precursor free, and we're really ready for mass production. We're taking a very interesting approach with our technology by seeking patent protection in some of the most impactful lithium-ion battery manufacturing or practicing jurisdictions. This includes Canada, the United States, Europe, China, Korea, Japan, among others. And we're very proud to say that last year, our initial all dry, zero waste cathode synthesis patent was granted in Japan with the reference given here. And it's my expectation that additional allowances are expected for that patent family as well as others over the next 6 to 12 months. So please do stay tuned. So this slide really illustrates an overview of what we are doing today. On the left-hand side of the slide, I'm showing some photographs of inside our pilot facility. The top left photograph shows our pilot scale roller hearth kiln, or RHK. It's a 13.5-meter long device with many, many heating zones to very adequately control the heating profile during calcination. And in the lower left photograph, I'm showing our 70 kilogram per hour pilot scale jet mill, which is housed within our 1,200 square foot dry room with an average dew point temperature of roughly minus 50 degrees Celsius on a good day. There's also some other assets that are inside of that dry room displayed in front of the pilot jet mill. And we've been doing this for a little while now. We've been working on all dry, zero waste cathode synthesis technology since 2020. That's when we truly began. And about the middle of 2023, we commissioned the assets I just went over on the left side of the screen, as well as others, to really be able to produce 10 tons per year, at least at a nameplate capacity, to demonstrate that, listen, you can make anything at the lab scale, but at the pilot scale, things start to get a little more real. To demonstrate relevancy and scalability of our technology, we truly needed to go to that next level up, which was the investment in this 10-ton per year facility. And what we're doing with that pilot line is really to produce materials to sample to a variety of tier 1 materials producers, cell manufacturers, and OEMs for their evaluation and acceptance of, hey, this material processing technology actually works and we would like to adopt it. That's the whole purpose of what we're working on today. And our commercialization plan is relatively simple. We're committed to a phased commercialization strategy that leverages our existing expertise in the material space to forge strategic partnerships and ongoing R&D to position our cathode active materials technology to really have as transformative an impact on the industry as possible. And we're doing that by building upon our successes and accelerating our commercialization through a few different pathways. The first is aligning our technology, what we can actually produce and what we're producing, to global market trends. So we're always trying to understand what materials are attractive to our prospective partners. We're also open to technology licensing and joint venture pathways and forging strategic development partnerships. All the while, we are leveraging government support and potential strategic investment in what we are doing on the ground today. So I mentioned partnerships on the previous slide, and this slide is illustrating two of our major technology partnerships that we have established in 2024. This is with CBMM on the left-hand side of the screen and Iconichem on the right-hand side of the screen. So for CBMM, we forged a joint development agreement that's focused on niobium materials for really enhancing the performance of our all-dry cathode materials. So CBMM is the global leader in the production of niobium specialty chemicals for a variety of applications, from steelmaking all the way to energy storage. And what we're doing with that agreement is really, that project is around using, involves using our process technology to synthesize, test, and analyze cathode materials that use CBMM's suite of niobium products to demonstrate an enhancement of electrochemical performance of those materials, or a more efficient process to actually generate the cathode active materials themselves. The joint collaboration agreement we have with Iconichem focuses on sustainable cathode material feedstock. So Iconichem in the UK is a world leader in the production and commercialization of cobalt and nickel salts. What we're working on with them is to collaborate on enhancing the recycling and reuse of critical minerals that can be used in lithium-ion batteries. We're using recycled feed in the all-dry zero waste process to really enhance the sustainability footprint of an already sustainable process. So I'd like to change gears a little bit and dive right into some technical case studies of materials that we have synthesized on our pilot line, and they really demonstrate that the materials we make are relevant and are competitive to commercially available single crystal NMC cathode powders. So we initially began this journey tackling a mid-nickel chemistry. We thought it would be an easy first step to demonstrate that the process works on a topical cathode chemistry. And what we initially began with was an NMC 631 product. This is a 60% nickel material where we combined, as I show on this slide, 60% nickel powder to 30% manganese powder, 10% cobalt powder, together with lithium carbonate and dopants all in a single step. And that combination of materials underwent the all-dry zero waste process. The resultant material is shown in the SEM images on the right-hand side of the screen, these beautiful single crystal particles. So there is a lot of data on this slide. I don't want to dwell too long, but if you do look at the left-hand side of the slide, you do see a table of numbers. For those who know what makes a good physical properties for an NMC material, you'll start to see some of these numbers make a lot of sense, and they're comparable to commercially available NMC 631 style powders. And the right-hand side of the slide illustrates just simple voltage curves and differential capacity from coin half-cell measurements made on this NMC 631 cathode powder. Something that comes up a lot whenever we discuss dry processing methods for NMC is how do we guarantee that we are intimately mixing all of the nickel, the manganese, and the cobalt within the powder. This is called intraparticle homogeneity. And we leverage the methods of SEM and EDX quite frequently to really do elemental analysis of multiple components of the powder to demonstrate that, yes, indeed, we are getting the atomic ratios of nickel to manganese to cobalt that we expect. And in the case of 631, like I'm illustrating here, you can see in the bar chart on the right-hand side for 10 independent points that we do indeed recover that 60%, 30%, 10% ratio of the metals. So I would say here that, at least for this sample, the regional compositional homogeneity is very good. So we can take these materials and do a head-to-head comparison in a standard, what we call torture test for these coin half-cell measurements that were done. And in here, we are comparing and contrasting the NOVONIX-made NMC 631 to a high-quality commercial NMC 631. And the cycling protocol is shown right to the right of my figure and about in the middle of the screen of what we're doing for each cycle. The electrode information is displayed in the text box to the right-hand side. What I really want to emphasize on this slide is when you compare the green open circles to the black closed circles, you see that our material is quite competitive to what could be purchased on the market today. This is one of the best NMC 631s that we have seen, and as such, this is why we use it as a benchmark for our own materials. We can see that especially in the prolonged 4.5 volt cycling from cycle 6 or 7 onwards, we are getting comparable discharge capacity, which is fantastic. This really defines the baseline for what all dry zero waste cathode processing can do for you. But we don't end in just simple coin cell measurements. We do have the ability through our Battery Technology Solutions division to construct our own pouch cells. In this case, I'm illustrating 1 amp hour stacked pouch cells, which were made using either the NOVONIX NMC 631 material or that commercial NMC 631 material. And we are pairing that against a well-known synthetic graphite called AML 400. And we're performing a few different test protocols on each of those cell types. Those types of measurements I mentioned earlier are either 25-degree cycling data at 1C rate or higher temperature 40-degree cycling at 0.33 C or C/3 rate. I'm showing here normalized capacity for each cell type. And what you start to see is that the material that we made at NOVONIX via all dry zero waste processing actually outperforms this commercial high quality NMC 631, both at 25 degrees Celsius as well as 40 degrees Celsius at the lower rate. So what you can really start seeing is all dry zero waste processing can give you a platform from which you could build upon to make a material that would meet your specific requirements, which is great. And you can do that at a lower cost without generating any waste streams. My next example is on an 811 material, where we push the envelope a little further and increase the nickel content to 80% and beyond. In this case, we're talking about 83% nickel NMC 811. And very analogously to my last example, I'm combining 83% nickel powder with 6% manganese powder and 11% cobalt powder. Now, instead of using lithium carbonate, I'm using lithium hydroxide as well as dopants in a single step. And after conducting the all dry zero waste process, you end up having, again, these beautiful single crystal morphology NMC 811 particles. And analogously to the last example, I have a table of numbers on the left-hand side. If you start looking at the numbers, you can say, hey, these make sense. These are values that I would expect for an NMC 811 material. And then the right-hand side of the slide, I have a voltage curve as well as coin cell cycling data, contrasting the NOVONIX NMC 811 powder to a high-quality commercial NMC 811. Here you see that our material, it's competitive, but it can be improved via either specialized dopants or coatings. Like I said previously, all dry zero waste provides a platform from which you can fully optimize a material to achieve the performance that you require for your desired application. The interparticle homogeneity of these materials for at least 2 different spots were measured by SEM and EDX. Rather than doing single point measurements over 10 or so particles, what is done here is a map of the characteristic signal from each of the elements, whether that's nickel, cobalt, or manganese. And we do not see any localized islanding, no localized bright spots of manganese in particular in this mix. So that indicates to us that the homogeneity of the metals in this powder are quite good. And again, it doesn't stop there. What we do is take that material, we assemble 1 amp hour stacked pouch cells, just like in the 631 case, and we test under very similar conditions to the 631 case, only we decrease the upper cutoff voltage a little bit. Rather than going to 4.3 volts, we're only cycling to 4.2 volts. So I'm showing many, many more cycles here in the case on the left-hand side for 25-degree cycling at 1C rate, and on the right-hand side of the slide, 40-degree cycling at a C/3 rate. And you can look at the normalized capacity and you see that we are indeed quite competitive at both 25 degrees and 40 degrees to the commercial reference. But this is not where it ends. You can always add in whatever dopant you so desire, whatever specialized coating you want to put on the surface of the material to enhance further the capacity retention of these materials. And I just want to end on a last, I would say, case study, which is done on an ultra-high 90+% nickel NMC. We call it the 95.5 series. So in this case, take 92% nickel powder, combine that with 2% manganese powder, 6% cobalt powder, again lithium hydroxide, and any dopants in a single step, conduct the all dry zero waste process to these materials, and out comes, again, these wonderful single crystal NMC 95.5 powders. And very similarly to the previous slides, the left-hand side of the slide has a table full of numbers with specific properties that demonstrate good 95.5 style material. On the right-hand side of the slide again, I have coin half-cell voltage curve in the top right, as well as some simple cycling data in the lower left. And you can see our material in green is demonstrating either similar or in this case, even a little better performance than the commercial NMC 95.5 material. Again, the homogeneity of the material, the nickel, the cobalt, the manganese are all very well intimately mixed within the powder. So that is going to lead to decent performance in a battery cell. And we, again, constructed 1 amp hour stacked pouch cells and conducted very similar test protocol to what I showed for the NMC 811 work, either cycling at 25 degrees Celsius or 40 degrees Celsius at 1C or C/3 respectively. So I want to illustrate something that's the importance of temperature control on your battery cells whenever you're testing. The left-hand side is showing actually room temperature cycling to around 1200 cycles, and then the cells were actually removed and put into a very well-controlled temperature temperature chamber at 25 degrees Celsius. And that's why the data for the NOVONIX material is so noisy up to cycle 1200, and it immediately flattens out as soon as you put it into a temperature controlled chamber. Nonetheless, when you look at these data at 1C, on the left-hand side of the slide, our material in green behaves very competitively to the commercial NMC 955 style material. And on the right-hand side of the slide, for the 40-degree data, it's pretty competitive. Again, it gives you the ability to define the baseline for the product and then add in whatever dopants you want. For the case of 955, it was a very primitively doped sample. So we have the ability to optimize around a dopant package, surface coating, whatever is of interest for the industry or for the partner. So I do want to end on a quick summary and wrap up this web-based seminar by going through a few items of what we discussed today. So we believe that NOVONIX technology truly does revolutionize cathode synthesis for the lithium-ion battery space. What I've demonstrated is that we can make NMC cathode powders that have performance parity for a range of chemistries from mid to ultra-high nickel components in a coin cell, in a full cell, etc. And I also mentioned that we have our pilot prototyping facility here. And on average, we're generating 20 to 50 kilos of product on our 10-ton per year pilot line pretty regularly. Some of our largest batches are 100 to 120 kilos. Really, the sky is the limit for us when it comes to the utilization factor of our equipment. And I do want to mention that the photograph on the right-hand side of the slide is actually a real picture from our RHK, our roller hearth kiln, with a set of 4 saggers or crucibles going through into the hot zone. We're also developing always and acquiring our technology patents in key jurisdictions, really because we have R&D in our blood. And we're in the process of establishing critical partnerships, both in the upstream and downstream sectors of the lithium-ion battery industry. And today we're utilizing our demonstration facility to sample materials that are custom made to prospective partners today. And with that, I'd just like to conclude my web-based seminar. And thank you very much for attending. And I'm happy to answer any questions that you may have. Thanks.
Thank you, Mark. Before we launch into the Q&A, just a reminder that if you do have any questions, to submit them using the Q&A button at the bottom of your screen. We have received some interesting questions, so I'll jump right in. The first one being, what purity and microstructure should the nickel or cobalt metal powders be? Two-part question. And will this not make the raw materials more expensive than sulfates?
You need raw materials from somewhere, right? When it comes to the purity of the materials that we do use in our process, we're very much focused on battery grade raw material feeds. So our nickel metal powders, for example, are a higher quality nickel powder. Same with our cobalt. When it comes to oxides, clearly we need to go into some specialty chemicals. However, the raw material cost, as we've kind of mapped it out, is competitive to what's out there today. When it comes to overall cost of the process and the products, these are things that we are working through right now to truly understand at a dollar per kilowatt hour what is the savings of all dry zero waste. So that's my comment there.
Okay. Is it possible to use all dry zero waste cathode synthesis also for common LFP material or the so-called LFP 4th generation?
Yeah, so all dry processing of LFP is inherently not new. It's not super novel. What I mean by that is there are a variety of different methods of making LFP that don't involve water already. After having said that, what we're working on today, the all dry zero waste process can be adapted and to make LFP. The question I always pose is, what is the cost of shaping the material after you already have it? If you do require a lot of milling steps, maybe beads milling or something else to get the morphology that you really want, that those processes themselves could be quite energy intensive. Making the base material isn't that difficult, but getting the sub-micron particle size that you desire for LFP may be challenging. There are some ways you can get around that, but right now we're focused on NMC.
What's the total energy usage of your process?
So that really depends on a lot of factors, in particular, the size of your facility. We're working through those numbers now with our engineering partners. So please stay tuned for more on that.
Back on your slide 7, is your flexible feedstock essentially throwing all your metals and dopants into a blender? And how do you maintain a consistent concentration as you make it into a CAM?
We have a variety of different pieces of equipment that we rely on to help us achieve homogeneity of all of the material in that combination step. I won't tell you today what our piece of equipment is that we favor, but if you do read some of the literature that's out there, in particular from Dr. Mark Obervach's lab, you can get an idea of the types of equipment required to perform similar all-dry processing of cathode active material. What was initially really published was work that was done on the so-called DPMG, dry particle microgranulation using mechanofusion. So that'll give you at least a starting point to look at how to combine the material.
What is the type of saggers used, and what is the reusability of saggers, and how do you discard the saggers?
So the saggers we're using right now are very standard, 330 by 330 by 110 millimeter in dimension. There are basically two types of saggers that are really, really well known and used in the industry. There's short saggers and tall saggers. In our furnace, we're compatible with the shorter style. Those materials, we get a similar life cycle to standard conventional cathode manufacturing. And how do we dispose of them? Right now, because we are at the R&D level, we stock them and then we send them out for hazardous waste disposal every few months. That's what we do. But in industry, that would be where I'll work with our engineering partners to understand a little bit more about how large scale waste is handled, like the saggers. Great question.
How cost competitive are all dry single crystals compared to conventional, comparing mid-nickel, high nickel?
Yeah, everything scales with your raw materials. Your process itself is largely fixed. Your operational cost will vary slightly depending on the materials you're making. Largely, that's due to the raw material cost. Your feed costs dominate the comparison between conventional to all dry process. Yeah, when we had the first process comparison study conducted, those numbers are given assuming an NMC 811 material at a 30,000 ton per year capacity. So that'll give you an idea of where that 30% on CapEx and 50% in OpEx really came from.
Any data on DCIR for the NMCs you have tested? And how does the DCIR of NMCs from dry process compare with the commercial?
I have those data, just not in this presentation. They're similar. I also didn't include delta V. We use polarization as a leading indicator of impedance growth during cycling. And in a lot of cases that I just showed on some of those capacity retention curves, you will see that our material, in terms of delta V at least, not DCIR, is lower than the conventional process or the same. But yeah, I do have DCIR measurements, just not in this PowerPoint.
Is dopant doing the magic of the rate capability?
Unknown. Dopants are actually quite a contentious topic. I know that you can put dopants into any material, but what does that dopant actually do? Whether that's a fundamental or application-based result, it's very challenging to tear that information out. What I will say is that our materials that do have dopants in them perform better than no dopants, but the same can be said about conventionally made NMC. We have a hydroxide-based precursor that we can lithiate with and without dopants, and we get similar types of enhancements by having a dopant within the material. So dopants are important, and more understanding into what dopants do, what surface coatings do, is always beneficial. So I would encourage people to work on understanding at a more fundamental level what dopants are doing within the cathode powders.
For the 1 amp hour pouch cells, why is the anode not using NOVONIX's artificial graphite?
When the project started, this is just what we had. So we had it on hand, on site, while our friends at the NOVONIX anode materials business were generating material. So this is just to get us started. And because we have so much of a history using this other AML 400 style graphite, that's what we used.
Are single crystal NMCs compatible with dry electrode processing?
Yes.
What are some considerations for all dry processing of different NMC types? For example, 50% nickel compared to 100% nickel.
Well, 100% can be done already all dry, because then you're not dealing with manganese and cobalt and trying to make that nice intimately mixed structure. There are considerations to make when you run between, say, a mid-nickel 50% product like a 532 all the way to, say, a 9T55. I would say one of the major considerations or differences is the heating profile. You're not cooking under the same conditions a mid-nickel product compared to an ultra-high nickel product. As well, the raw material feeds can be mixed and matched between a mid-nickel product and an ultra-high nickel product. So essentially, you can use the same materials in both. However, it may be easier to use one or another depending on the material that you're interested in really ultimately making and using.
Lots of good engagement here. More questions. I believe most high nickel NMC materials are coated for improved high voltage stability. Are your high nickel NMCs coated as well? And if so, how do you apply the coating?
Yep. So all of the materials that I showed in my presentation, they do have a very, very primitive surface coating. So it's no surprise that aluminum oxide is a very common surface coating material for NMC. The same comment I made about dopants can be said about coatings as well. A lot of fundamental work needs to be done on surface coatings to truly understand what each really does, and what that resultant benefit is in a battery cell. So my materials that I demonstrated today do have a very simple aluminum oxide surface coating, and we apply that in a dry state. We are not experts in surface coating. What I'm showing today is that we can give a platform using our technology on which that can be built upon to enhance either high voltage stability, rate capability, etc. This is the platform for next gen cathode synthesis. All of the other processing steps, for example, surface coating, other surface treatments, the base material itself is quite compatible with whatever you want to put on the surface. And the commercial materials, I should mention, So we do not necessarily have access to the dopant loadout or the surface coating on those materials. But I will say that every commercial material I was comparing against in the presentation did have a truly optimized surface coating as well as a truly optimized dopant package. So if we can match their material, their performance in any aspect, then we're doing it all right and demonstrating that the platform technology really does work and enable next-gen cathode production.
Recently, LG released a major PR about their precursor-free cathodes, branded as LG precursor-free LPF. This has caused some confusion with LFP, but it appears to be precursor-free NMC. How does this differ from what NOVONIX has been doing for a while? Is it similar to NOVONIX's approach or different?
So the real answer to that is I don't know. You would have to ask LG Chem and try to dig into their literature and what has been reported. So I would encourage that. I know that's not a very satisfactory answer, but truly, I don't know.
Do you plan to build a CAM plant?
So that's an option. When I went over the commercialization slide, I was really emphasizing the fact that we really want to forge either licensing opportunities or partnerships, as well as joint venturing. While it's not out of the question that we will not build out a CAM processing facility, it is a lower priority right now on our development timeline.
And circling back on the sagers, are they made of graphite or other?
They're standard ceramic, so they're not 100% alumina. The vendor provides a full suite of standard cathode active material, Sager ceramics, and that's what we use.
Great, thanks, Mark. That ends our Q&A session. Thanks so much for your presentation today. For everybody else on the call, thank you so much for joining us today and for your great questions during the Q&A. We hope you found the session informative and insightful, and this recording will be made available on the NOVONIX website. As I mentioned at the beginning of the call, this is just the beginning of our webinar series. We're looking forward to continuing the conversation with our upcoming sessions on prototyping and testing evaluations, which will take place on April 30th. And there's one on May 14th on our ultra-high precision coulometry equipment. You can find registration links on the NOVONIX website or on our LinkedIn page. On behalf of the entire NOVONIX team, thank you once again for being here. If you have any follow-up questions or would like more information, please don't hesitate to reach out. Have a wonderful day.
Thanks, everyone. Bye-bye.